Till now, we have considered the filtering in the spatial domain or image enhancement using the spatial domain. Now we will talk about the image enhancement or filtering in the frequency domain. Okay. So first we will go through the basics, what each one of this will correspond to, and then we can talk. So what is Fourier transform, what is Fourier series, and all that we'll see. And using those Fourier transform, we will see the filtering. Okay, frequency domain just means Fourier transform only. So Fourier series and Fourier transform are basically due to Jean-Baptiste Joseph Fourier, who is a French mathematician and physicist, who was between 1768 to 1830. So orphaned at 9, Egyptian expedition with Napoleon I in 1798. Then he became the governor of Lower Egypt, then permanent secretary of the French Academy of Sciences, 1822. And 1822 itself, he wrote a book, a treatise, which is known as Theorie analytique de la chaleur. That just means the analytic theory of heat. And this was the pioneering work which talked about the Fourier series and Fourier transform. Okay, this looks more like the mechanical engineering, but really speaking, it we know very well that the Fourier series and Fourier transform are the one which are the mainstay of the communication. So Fourier series is any periodic function can be expressed as a sum of sine and or cosines of different frequencies, each multiplied by a different coefficient. Okay, any periodic function can be represented by a constant, a fundamental frequency, and its harmonics. That's another way of writing the Fourier series. Okay, the Fourier series is nothing but any periodic function can be represented by a constant, a fundamental frequency, and its harmonics. And this representation of a periodic function by means of all these terms, that is a constant, a fundamental frequency, and its harmonics, is known as the Fourier series. The other way of telling it is sum of the sines or cosines of different frequencies, each multiplied by a different coefficient. So when we talk about periodic function, we talk about Fourier series. But when we talk about a non-periodic function, then that can be expressed as, so the sum is removed over here and we try to write the integral. Integral of sine and or cosines multiplied by a weighting function or coefficient, whatever you call it. So here we have sum, here we have integral. That's the only difference. So when the sum changes to integral, then it becomes from Fourier series to Fourier transform. And Fourier series is for periodic function, Fourier transform is for non-periodic functions. So this is how the Fourier series looks like. You have some frequency, double of that here, 4 times of that here. Might be something like 16 times here and so on. So this is also a periodic function. Okay. So all these are periodic because they are repetitive. Periodic just means they are repetitive with respect to some particular period. Okay, all these might be sinusoidal, but this is not sinusoidal or cosinusoidal, whatever you call it, but it is periodic. Now let us take some preliminary concepts. That is, j is equal to root of -1 is a complex number. We know very well. I or j equal to root of -1 is a complex number, and a complex number can be written as a complex quantity over here. J is a complex quantity, and a complex number can be written as c is equal to r plus gi, where r is the real part and I is the imaginary part for a complex number c. Its conjugate, which is written as c star, is equal to r minus ji. Again, r and I refer to the real part and the imaginary part of the whatever complex number we have. Minus sign is the conjugation. Here it is plus, here it is minus. Then we write here for this C, the magnitude of C as root of r squared plus I squared, and the angle associated with this C is theta equal to arctan I by r, arctan of the imaginary part divided by the real part. Therefore, the value of C can be written as magnitude and cos of theta plus j sin theta, and cos of theta plus j sin theta is the situation over here where theta is equal to arctan I by r. This cos of theta plus j sin theta can always be written as e to the power of j theta using the Euler's formula. So C is equal to mod of C e to the power of j theta. So coming back to the Fourier series, a function ft of a continuous variable t that is periodic with period t can be expressed as a sum of sines and cosines multiplied by the appropriate coefficients. Okay, and that sine and cosine together can always be written as a combined entity where we can write Cn is equal to e to the power of j 2 pi n t t. So this is cos theta plus j sin theta is e to the power of j theta. And this is Cn over here, where Cn is 1 by t integral minus t by 2 to plus t by 2 f of t e to the power of minus j 2 pi n t by capital T dt, where n can take any values from 0 plus or minus 1 plus or minus 2, etc. So you have a summation here. That's why it is a Fourier series. Do not get confused with this. This is only how to calculate the value of Cn, how to calculate the values of Cn. Whereas this is the function which is ft, which is nothing but a continuous function, and hence this should be summation. Then we come to the impulses and the shifting property. Shifting or shifting both refer to same. H might be missing over here. A unit impulse of a continuous variable t located at t equal to 0 is denoted by del t, is defined as delta t is equal to infinity if t equal to 0 and 0 if t not equal to 0. However, there's a constraint that the del t has width which is very, very, very small or equal to 0 itself. Hence, in the limiting case, we have the integral of minus infinity to infinity del t dt equal to 1. Okay, this identity condition is satisfied because the height of del t is infinity at t equal to 0, but the width itself is 0 itself at t equal to 0. So therefore, in the limiting case, the integral of that del t dt will be equal to 1. Now the shifting property just indicates that if you multiply this del t by ft, then this 1 will be multiplied by f of 0. If del t is multiplied by f of t, then this 1 will be multiplied by f of 0. Now also, if you shift this del t by another value which is minus t naught, then in place of f of 0, we'll get f of t naught. So here we have, you can say that we have something like t minus 0, whereas because of that, this will give you the value of f of 0, whereas here you have t minus t naught. So therefore, this will become, this quantity equated to 0 will give you t naught. Now coming to the unit impulse of a discrete variable x located at x equal to 0, we define it as del x is equal to 1 if x equal to 0, 0 if x not equal to 0. So try to see the difference between these two. Here it is, del t is equal to infinity if t equal to 0 and 0 if t not equal to 0. And integral of that is equal to 1. Whereas when we talk about the discrete, then del x is equal to 1 if x is equal to 0, 0 if x not equal to 0, and is constrained also to satisfy the identity sigma minus infinity to infinity del x is equal to 1. The shifting property associated with this will be, if you multiply with del x the value of fx, then we'll get f of 0. And extending it further, if you take here del of x minus x naught into fx with a sigma value here, now here you have x minus 0, therefore this is f of 0. This is x minus x naught, therefore it is f of x naught. Because here del of x minus 0 we have, this is f of 0. Here we have del of x minus x naught, therefore this will be f of x naught. Okay, both the places fx is remaining same. Fx is shifted, then equally the rest of the thing also will be shifted. Then the impulse train is represented like this. The impulse train is a set of impulses which are, away by from each other by the del t, that is periodic with respect to del t. Impulses which are periodic with respect to del t is generally written as s of del t dt, and that's how we have here 0 to del t. Difference between these two samples. Over here is del t, here also del t, here it is del t, here it is del t from each to the other. 2 del t minus del t, 3 del t minus 2 del t, and all that. Okay, it is a del t difference. So this is a periodic impulse train. The Fourier transform of a continuous function f of t is generally written as f of mu is equal to Fourier of f of t equal to minus infinity ft e to the power of minus j 2 pi mu t dt. Generally, we might have taken f there for mu, but so as not to get confused with this ft and this f over here, we have written mu here in place of f. So the inverse Fourier transform of f of mu is f of t is equal to f inverse of f of mu is equal to minus infinity f of mu e to the power of j 2 pi mu t d mu. So here it is e to the power of minus j 2 pi mu t del t, whereas here it will be e to the power of plus j 2 pi mu 2 pi mu t. For the inverse Fourier transform, this will become positive rather than the negative value over here. So if we take one continuous variable, what will be the Fourier transform corresponding to this? So if we take f of t something like this, which is a window function, it has a constant value a between minus w by 2 to plus w by 2, then what happens to its, Fourier transform? So f of t is equal to, f of mu is equal to integral minus infinity f of t to the power of minus j 2 pi mu t dt. So in place of this, you can see that for a window function only between these two, it is a, rest of the time it is 0. So therefore it is minus w by 2 plus w by 2 a e to the power of minus j 2 pi mu t dt. A is constant, you can take it out, you can integrate it, with respect to t, this particular quantity that will give us the value, minus a by, so to say, j 2 pi mu e to the power of minus j 2 pi mu t with limits minus w by 2, w by 2. E to the power of minus at will be equal to the integral of e to the power of minus at will be e to the power of minus at divided by minus of a. So that's why this minus sign is coming, and this value is coming as j 2 pi mu, which is the coefficient of the value t. So then w by 2 and minus w by 2 you can substitute in this limit, giving us this value, and this is nothing but, again, we can try to write it here, 2 pi mu multiplied by, again, 2 pi mu. So that will give us, you can convert this into a sine function. So SW sine of pi mu w divided by pi mu w. Okay, so this will be the function. This whatever we have will be equal to this over here, because you can take inside the value pi w over here. Okay, and 2 also, 2 pi w over here. If you take 2 over here, then that will become the sine function, right? Then we'll be left with the a divided a multiplied by the sine of whatever we have, pi mu w divided by the values which remain will be, 2 has gone, and j also will go for sine, because sine theta is equal to e to the power of j theta minus e to the power of minus j theta divided by 2j. So j2 I should take over here. So what remains is the value pi w. Okay, pi w. So for this pi w, you should multiply by, what you call the corresponding, oh sorry, this is not w, this is rather mu. There's a mistake here. This is mu. So therefore, my WW, you multiply numerator and denominator, you are left with this. Now this is again a sinc function. This is a sinc function. AW sinc pi mu W. Now that will look something like this. Sinc function will look something like this. Simple function, its Fourier transform and spectrum. Spectrum is, modulus of this. That means whatever is negative will also become positive. So all the things which are there here below this line will get inverted in the, so to say, mod function. That's why we'll have here. So spectrum is just the mod function of the Fourier transform which can be found. So Fourier now, till now we consider the Fourier transform for one continuous variable. Now we'll talk about the Fourier transform of impulses. So Fourier transform of a unit impulse is minus infinity to infinity del t to the power of minus j 2 pi mu t dt. Now this will be naturally t equal to 0. If you write, then this value will be, in the limiting case, it will take care of itself. Integral of that will become 0. But if t is not equal to 0, this quantity becomes, total quantity becomes 0. So therefore, we'll have e to the power of minus j 2 pi mu. In place of t, I should write t equal to 0 because only del 0 is equal to 1. All other dels are not equal to 1, that is equal to 0. So this quantity is equal to 1. So if you have a unit impulse, if you take the Fourier transform of that, you're going to get a value 1. So Fourier transform of a unit impulse located at t equal to t naught can be written like this, and this quantity over here will be equal to 1 at t equal to t naught. At all other places it will be 0. So therefore we will get this as e to the power of j minus j 2 pi mu t naught, e to the power of minus j 2 pi mu t naught. And that is nothing but cos of the 2 pi mu t naught minus j sine of 2 pi mu t naught. So impulse response will have the Fourier transform, which is something like this. Then the impulse train is just a periodic set of impulse functions and so to say impulses, periodic set of impulses which are separated by del t over here. This we have already seen, and we can write it. Impulses can be written something like this because this is del t, this is del t minus del t, this is del t minus 2 del t, this is t minus 3 del t. Definitely this will be del t plus del t. This is del t plus 2 del t, this is del t plus 3 del t, and if you write all of them in the summation form, then that will become n equal to minus infinity del of t minus n del t. So the Fourier writing the Fourier series for this impulse train, then you'll get sigma of n equal to minus infinity cn e to the power of j 2 pi n del t into t, where the value of Cn will be 1 by del t, integral minus del t by 2 to del t by 2, the s of del t of t into e to the power of minus j 2 pi n by del t into t dt. So Cn will be 1 by del t. You can just try to integrate all that, right? And substitute, whatever we have written in the form of the summation, uh, you know, of all that, and then you can try to simplify that, and then you'll get 1 by del t to the power of 0 equal to 1 by del t. So the value of Cn is 1 by del t over here. So you can just replace the Cn by 1 by del t, sigma of e to the power of j 2 pi n by del t into t. So this is how the impulse train looks like. This is s of del t into t. Okay. So uh, for this, right? For this, if you take the Fourier transform, uh, then you'll get equivalently the Fourier transform of this, because this cannot have a Fourier transform. So Fourier transform of this is considered first over here, and we can substitute in the Fourier transform formula and try to expand it, and then you'll get del of mu minus n by delta. So effectively, the Fourier transform of this function would be 1 by del t sigma e to the power of j. For this we need to write the Fourier transform of this, right? So the inverse Fourier transform of this function will be naturally the one which we have written over here. Okay, same thing is being mentioned over there. So let S mu denote the Fourier transform of the periodic impulse train S of delta t. Then we can try to write that and then take the Fourier transform of this function from the earlier slide and substitute from there. So in place of this, we have the value of sigma del mu minus n by del t. Okay. So that's what we have over here. This, in place of this, we have this summation remains as it is. Then we have how the Fourier transform and the convolution are connected to each other is what we will try to see over here. So the convolution of two functions is denoted by the operator, which is a star over here, and ft convolution st is equal to minus infinity to infinity f of tau h of t minus tau d tau. This we have already studied in signals and systems, and then in DSP and many other places. Now the Fourier transform of the convolution is nothing but Fourier transform of the convolution in the frequency domain is equivalent to the multiplication in the frequency domain, and that's what we will get over here. And that again we have studied in signals and system. It is just a review of all those topics over here. So Fourier transform of this will be this with the whatever we have written in the convolution, and then e to the power of minus j 2 pi mu t t t. So we can just, what you call delta you have here, and, dt we have here, and we can take this here, and dt over here. T is associated only with H. It's not associated with F. Hence, F of tau is taken out, and then integral, you have taken here for T, and delta is taken out outside. So it is just, we are trying to change the order of integration. And this quantity, if we try to solve, then we'll get h of mu e to the power of minus j 2 pi mu tau d tau. Okay, this is the term which we'll get for whatever is there. D tau will remain as it is. F of tau will remain as it is. This is the integration, because we have a shifted format of ht minus tau e to the power of minus j 2 pi mu t will give us this itself. So h mu is not associated with tau, hence it's taken out, and we are trying to write this, and this quantity is nothing but f of mu. So the convolution in the time domain is equivalent to the multiplication in the frequency domain. That is what this function says. So thus you have the convolution of time functions in the will form one Fourier, one of the Fourier transform pairs, the other pair being the multiplication of the two functions in the frequency domain. So this just gives us that they are the Fourier transform of each other. Similarly, the multiplication in the time domain is can be represented by the so to say convolution in the frequency domain. So now we can what you call talk about here. Now this figure gives us that we have a what you call continuous function ft, right? We take the samples of this by passing a Fourier so to say impulse train, and that will give us the sampling function, and the samples at different places is for here at different points here. Okay, so continuous function, train of impulses to model the sampling process. C is the sampled function formed as the product of A and B. Then D is the sampled values obtained by integration and using the shifting property of the impulse. So the dashed line in C is shown for reference. It is not part of the data. Okay, this is just dashed line. So only this point, this point and this point, all the points are shown on this. So Fourier transform of the sampled function, you can just take f of mu equal to f of ft, and this is the sampled function ft multiplied by the impulse train. What will that give? And that is nothing but the what you call convolution. Here we have multiplication in the time domain. We have convolution in the frequency domain, where the f mu is the Fourier transform of ft and s of mu is the Fourier transform of s del t, which is nothing but the impulse train. So S mu is 1 by del t sigma of n equal to minus infinity to infinity del of mu minus n of n by del t. Right? So we can try to write all that. F hat mu is equal to F mu into S of mu. F hat mu is the Fourier transform of the sampled function. The sampled function is represented like this, and that is, in the frequency domain, that is this. And we can try to write all that, and we will get at the end this quantity. So you can compare this F mu with S mu. S mu is 1 by del t del of mu minus n del t, whereas F mu with a hat will be del is replaced by F. Del is replaced by F. So if you simplify this, you are going to get this function, which is similar to this, whatever we have written here, except that in place of del, we have F. Okay, all other terms being same. So the question is here, we have a question here, the Fourier transform of a sampled function shown in the following figure is continuous or discrete, whether this value is continuous or it is discrete. Can somebody tell what it is?